Those are the early discoveries. We've learned enough to characterize small things that orbit around very large central bodies. The planets are very small compared to the Sun. Artificial satellites and even the Moon are very small compared to the Earth. Orbital elements allow us to unambiguously specify the specific path a body takes around a very large central body. Something in motion around a central body in 3 dimensions has 6 degrees of freedom. They're shown here. I'll go through this in detail and then we'll come back to this diagram. First, let me show you why there's 6 degrees of freedom. The first is the semi-major axis, or in this case, the radius of the circle. Once we've sized the orbit, we can change the shape. We can give it some eccentricity. That's the second degree of freedom. Now we have an ellipse. Next, we can rotate the ellipse around the z-axis. We're rotating it here in the xy plane. We can also flip the ellipse along the x-axis, or along the x and z-axis. And then we can rotate it along the y-axis. That's not how we orient orbits, though. We start with a rotation around the z-axis, like this. And then we make a rotation about the x-axis, like this. So you can see the orbit has some tilt to it, which we call inclination. Now, in order to do this last rotation around the z-axis, we need some reference lines. So we'll draw these lines about the x-axis called nodal lines. And do the last rotation. And now you can see the nodal lines rotated with respect to the x-axis. With these 3 rotations, we can orient this ellipse in any orientation in 3-dimensional space. In order to orient an orbit, we need a reference point. Let's start with the Sun. The disk here that emanates out from the Sun is the plane of the ecliptic. That's the plane the Earth orbits in. This is the reference plane for objects that orbit the Sun. Here I've inserted the Earth. Its equatorial plane is tilted 23.4 degrees with respect to the plane of the ecliptic. Objects that orbit the Earth are in reference to the Earth's equatorial plane. Here's another view. Note the line of intersection between the Earth's equatorial plane and the plane of the ecliptic. This orientation would be at solstice, either the start of summer or the start of winter. A solstice is where the intersection between the ecliptic and the equatorial plane is orthogonal, or at a right angle to the Earth position vector that extends between the Earth and the Sun. As the Earth spins in this orientation, the day and night are 12 hours everywhere. This orientation is at an equinox. The intersection of the ecliptic and the equatorial plane is in line with the Earth position vector. During the vernal equinox, the line from the Earth to the Sun points to the constellation Pisces and what used to be the first point of Aries. Here's another graphic that shows this. The line formed by the intersection of the equatorial plane and the ecliptic always points to the constellation Pisces. The primary reference point for locating objects in space is the constellation Pisces and is referred to for nostalgic reasons as the first point in Aries. Here's a more realistic image of the Earth, its equatorial plane, and the Sun. This is set at the vernal equinox. Look at the blue vector coming from the Earth. That points to the vernal equinox point, which is where the Sun is at the vernal equinox. We call this the Earth vernal equinox vector. No matter where the Earth is, this vector points to the same point in the sky, the constellation Pisces. As I rotate the image, you'll see that the Earth vernal equinox vector points directly at the Sun at vernal equinox. The green plane is the plane of the Earth's equator. It's fixed in inertial space. That means it isn't moving. Notice that the stars in the background are still relative to the equatorial plane. The purple is the equatorial grid. And you can see the Sun moving from the 0, 0 point as it moves to the left. It's moving through the constellation Pisces. An ancient astronomer, Hipparchus, discovered that the equinox points are precessing. In the past 4,000 years, the vernal equinox has traveled from the constellation Taurus to Pisces and is headed to Aquarius. If you're a product in the 1960s, you remember a line from a song by the Fifth Dimension that was in the Broadway play Hair. This is the dawning of the age of Aquarius. This is what they meant. The vernal equinox is moving from Pisces to Aquarius. That fixed reference point used to point to Aries. That's why it's referred to as the first point of Aries. The precession of the equinoxes occurs because of the wobble in the Earth's orbit. Things that spin tend to wobble. This animation shows how we locate points on the Earth. You're familiar with latitude and longitude. 10 degrees north forms a parallel, then encircles the Earth. It's the thin blue line. As you move the point farther and farther north, the thin blue circle gets smaller. At 90 degrees north, you're at the North Pole, a point on the Earth, a single point on the Earth. 10 degrees west forms a circle along the dark blue line that encompasses the circumference of the Earth. And that would be here. Western latitudes are west of the prime meridian. Eastern latitudes are east. East meets west at the international date line. At the poles, longitude becomes ambiguous. The 0, 0 point is just off the coast of Africa. Objects in the sky are located in a similar way. Imagine a celestial sphere with the stars on it. This isn't how the stars actually are. Their distances from us are quite different. They do, however, appear to us as if they were on a sphere. That makes locating them simpler. The equivalent of latitude is declination, and the equivalent of longitude is right ascension. Here we see somebody at 0 degrees latitude at midnight looking straight up. The point they see in the sky is 0 degrees of declination and 0 hours of right ascension. That's the vernal equinox point that points to the constellation Pisces. If the declination increases, the object approaches the northern horizon. If the declination decreases, the object approaches the southern horizon. If the right ascension increases, the object approaches the eastern horizon, and if it decreases, the object approaches the western horizon. We can locate any object in the sky with this coordinate system. So here's an increase in declination, and here's a decrease, and here's an increase in right ascension, and a decrease. This animation shows you what the celestial sphere looks like and where stars really are. We see the Big Dipper as a constellation. In reality, the stars are at different distances from the Earth. If all we want to do is locate stars in the night sky, then a celestial sphere analogy works. The ancients actually thought stars were on a sphere. Today we know that's not true. This puts the previous animation in perspective. The left pane is a view of the celestial sphere from above. The right pane is a view from the celestial sphere from above. The left pane is an observer's perspective. Notice the map on the lower left. I'll put the observer at the 0, 0 point, right here off the coast of Africa. I can rotate the Earth's perspective so that it rotates in a way we're familiar with. And then I'll add some stars. This is the path the stars would take in the night sky for an observer at that point in the Earth. Now watch what happens if I move to a northern latitude. Here, this person can see the Big Dipper, but can't see the Southern Cross. And the constellation Orion, being on the equator, rises and sets along an arc. If I put the observer in South America, the observer can see Orion along an elliptical arc. They can see the Southern Cross, but can't see the Big Dipper. So suffice it to say, this system of right ascension and declination allows us to locate any object in the sky from anywhere on Earth. Let's now go through the degrees of freedom more formally. We'll start with a circle. Here we've chosen a semi-major axis A. The x-axis points to the first point of Aries, and the plane of this circle is in the Earth's equatorial plane. We want to give the orbit some eccentricity, which we call epsilon. This is the second degree of freedom. Let's draw the ellipse with a major axis line. This line is coincident with the x-axis and points to the first point of Aries. The next degree of freedom involves a rotation about the z-axis. Notice the line that extends from the focus to the periapsis point on the red ellipse. We call that the argument of periapsis. The rotation omega is the angle between the blue semi-major axis line that points to the first point in Aries and the red line of periapsis. This is the third degree of freedom. Now we want to give the red ellipse some inclination. To do that, we'll rotate the ellipse about the x-axis. It rotates about the nodal line that's in line with the x-axis. We're going to rotate or tilt the red ellipse along that red nodal line. The purple ellipse is the red ellipse tilted. This is called inclination. The angle of tilt is denoted by the letter I. Here's what inclination looks like from different perspectives. This is the fourth degree of freedom. The last rotation is about the z-axis again. It's another rotation in the xy plane. For that, we need our first point of Aries, our point of reference again, the first point of Aries. This rotation will be denoted with the big omega character. See how the nodal line is shifted. We call this rotation the right ascension of the ascending node. You all know what right ascension is, and I'll tell you what ascending node is in a minute. This is the fifth degree of freedom. Our rotations are now complete. We rotated first about the z-axis, then about the x, and then about the z again. This is the convention for orbital elements and can position the ellipse in any orientation. And here's the orientation from different perspectives. The last degree of freedom is the location of the orbiting body along the ellipse, the true anomaly. Let's go through this again with a more realistic animation. This is the simplest orbit. The eccentricity is 0. It's a circular orbit. The true anomaly is the angle between the satellite position vector and the periapsis line, which was our last degree of freedom. The argument of periapsis is 0. That means the periapsis line is lined up with the first point of Aries. There's no inclination. This orbit's in the equatorial plane, and that's synonymous with the xy plane. And the right ascension of the ascending node is ambiguous for an orbit with no inclination. Here we're showing the first degree of freedom. The semi-major axis is equivalent to the radius of the circle. Here we exercise our second degree of freedom. We give the orbit some eccentricity. Note the change in the velocity of the satellite as the true anomaly changes. The true anomaly timing now follows Kepler's second law, where equal areas are swept out in equal time. Let's add proper shading. Umbra is the term for the area in total shadow. Penumbra is the term for the area at the transition between light and total shadow. From our perspective on Earth, umbra is synonymous with night. Penumbra is synonymous with twilight. In this animation, you can see the portion of the Earth that is in the sun's shadow. The red portion of the ellipse is the portion of the orbit where the satellite is also in the Earth's shadow. The Earth orbits the sun, so the umbra region moves over time, while the orbital reference stays fixed in inertial space. Here we've shifted the argument of perigee by 45 degrees. Notice that the red region of the orbit where the satellite is in the Earth's shadow has shifted. The orbit is still in the equatorial plane with no inclination. Here we shift the argument of perigee back to 0 and add 45 degrees of inclination. We've added back the radial lines for the equatorial plane so you can see the inclination more clearly. Here we've moved the right ascension of the ascending node. Notice that there's no longer a red portion of the ellipse. In this orientation at this time of year, the vernal equinox, the satellite stays in the sun for the entire orbit. This animation illustrates the nodal points. They are the points where the satellite intersects the equatorial plane. If the entire ellipse or orbit were in the equatorial plane, these points are ambiguous. That's why we need some inclination in order to change the right ascension of the ascending node. When the satellite is traveling from south to north, we say it's ascending. When it travels from north to south, we say it's descending. As I said earlier, we need to pick one of these nodal points for the point of right ascension. The convention is to use the ascending node. That's where the term right ascension of the ascending node comes from. In this animation, the ascending node is coincident with the periapsis point. Here we've rotated the periapsis point 45 degrees in the plane of the ellipse. The satellite crosses the equatorial plane on the ascending side at the point labeled line of nodes. The periapsis point is rotated 4 pi radians from this point. The line of nodes is also rotated 4 pi radians from the Earth vernal equinox point. And the ellipse is rotated 4 pi radians around the line of nodes line. Those are the 3 rotations. Take note of the blue light line drawn on the Earth. That's a projection of the elliptical orbit at this orientation. It takes into account the spin of the Earth. From this point of reference far away, the path of the satellite is a regular elliptical form. Projected on the Earth, however, it follows a circuitous path. Let's look at this point from the view of the satellite. The red line is the position vector from the satellite's perspective, and we call this the nadir vector. From this orientation, the ground track caused by the combination of the Earth's rotation and the elliptical orbit makes no sense. Let's try a fixed Earth perspective. Let's say we lived in North Africa. Here's how the satellite would appear to us. If we wanted to figure out the orbit, we need a collection of observations all over the world. The revisit time, that's the time between instances where the satellite is overhead, is a couple days or longer. Also, then we need a way to observe the satellite during the day when the sky is lit up. If I put us on the Earth looking up at the sky, here's what we'd see. The satellite's moving relative to the stellar background. A few days later, we'd see this. By the way, these satellites or planets don't make these nice blue lines in space. They're little dots. Here again is the pictorial representation of the orbital parameters. Eccentricity, denoted by epsilon, determines the shape of the ellipse. A is the semi-major axis. The rotation of the periapsis point is denoted by little omega. It's called the argument of periapsis. The tilt of the ellipse from the plane of reference is the inclination, denoted by I. In order to swivel the ellipse at this point, we need a reference direction. We'll call that the first point of Aries, and it's denoted by this little ram because Aries is a ram. The angle from that to our nodal lines at the ascension point is the longitude of the ascending node, or the right ascension of the ascending node. Here I'll show you how orbits vary as we vary each of the degrees of freedom. Here's a simple form of true anomaly. It's the location of the satellite for a given time. Here I'm showing you orbits with offset true anomalies. All the orbits are identical with the exception of when the satellite crosses the equator. You can see in the 2D plane that since the Earth rotates underneath these orbits, the coverage of each satellite is different. Here are orbits with different semi-major axes. The timing of these orbits follows Kepler's third law. The outer objects travel both longer and slower. These are orbits with differing eccentricities. They go from 0, which is circular, to 0.74. Notice that the periods of these orbits are all the same. The semi-major axes are all equal. Kepler's third law stipulates that the periods must be the same. Here, we've taken elliptical orbits and changed the semi-major axis again. Notice that the periods of these orbits differ. Here's a shift in the argument of perigee, and each of these are offset by 90 degrees. And here's what an inclination change looks like. A highly inclined orbit is called a polar orbit. A zero inclination orbit is called an equatorial orbit. And here's what inclination looks like on a Mercator projection. If you want full coverage of the Earth, you'll want something closer to a 90-degree inclination. Low inclined orbits only cover a narrow band of the Earth along the equator. Here's a polar orbit with a 90-degree inclination. Inclinations higher than 90 degrees are called retrograde orbits, since the rotation goes counter to the rotation of the Earth. Here we shift the right ascension of the ascending node. The satellites all cross the equator at the same time, however they cross at different points. Given these orbital parameters, we can put satellites in different orbital regimes. The common ones are low Earth orbit, LEO, medium Earth orbit, MEO, highly elliptical orbit, HEO, and geosynchronous orbit, GEO. This is a geosynchronous orbit. According to Kepler's third law, the speed of an orbit slows down as the satellite gets farther from its central body. This orbit has a semi-major axis of 26,199 miles, or 42,164 kilometers. That equates to an altitude of 22,240 miles, or 35,793 kilometers. You can see from the Mercator projection that the satellite footprint is fixed. Here's what a geosynchronous orbit looks like with some inclination. You can see on the Mercator 2D map that the satellite footprint moves up and down. So this is not very good if you want to cover the higher parts of Canada full time. If you want to access higher latitudes, geosynchronous orbits don't work. For areas like Russia, we use highly elliptical orbits. Here's an example. You can see that the satellite reaches Russia on one pass and then Canada on the next. Since these are elliptical, they have a perigee and an apogee. Perigee is typically 1,248 miles. Apogee is typically 24,233 miles, which is similar to geosynchronous orbit. The orbital period is 12 hours. So at perigee, the satellite is not of much use. It's very close to the Earth and is moving very fast, 20,132 miles per hour. You need 3 HEO satellites to get full-time coverage in the northern latitudes. You can see in this animation that one satellite is ascending when the next one descends. So as this one descends, we send another one up. Then that one goes and services Russia. When the yellow descends, we send the red one up. Then yellow hovers over Russia. And so on. Life is good if you're on the equator. We can launch one geosynchronous satellite to service an area for years. At the northern latitudes, we need 3 satellites. This is a medium Earth orbit. Altitudes range from 1,200 miles to 21,748 miles. In other words, it's between LEO and GEO. And I'll talk about LEO in a minute. Orbital periods start at 2 hours and go up to 23.5 hours. This is what the GPS constellation looked like many years ago. Because the inclination of a polar orbit is 90 degrees, a satellite in polar orbit will eventually pass over every part of the world. This makes polar orbits well suited for satellites gathering information about the Earth, such as weather satellites. Altitudes range from 160 kilometers to 2,000 kilometers. At their lowest, orbital periods are 88 minutes. At their highest, they're 127 minutes. Thus, in this regime, it takes 1.5 or 2 hours to completely orbit the Earth. Low Earth orbits are good if you want to be close in. You can see things better, but you lose the perspective you get at higher altitudes. This animation shows a low Earth satellite with occasional ground contacts. The contacts are short. If sensors collect lots of data, there must be onboard storage. Relay satellites overcome that. They can be in almost constant contact with low Earth orbiting satellites and, as well, can be in almost constant contact with ground station. This gets data down quicker but is expensive. NASA has a relay program called TDRS. Orbits, here are the orbital regimes. LEO is low Earth orbit, MEO is medium Earth orbit, and GEO is geosynchronous orbit. And here they are depicted as animated. The purple is HEO, the orange is MEO, yellow is LEO, and green is geosynchronous. This is a transfer orbit from Earth to Mars. Every 26 months, probes can be launched to Mars. Other times a year, it would take significantly more energy, which means a larger rocket. This probe is launched in an elliptical orbit around the Sun. The perihelion